So we were still in the middle of trying to show that the inverse function theorem can be applied to our function capital F. This was capital F. And in order to verify the hypotheses of the inverse function theorem, we had to verify that capital F is a C1 function, and which we have done. We did that in the last video. And we need capital F prime of x naught y naught to be invertible. Okay, so this is what we're going to work on in this video, invertibility of this linear map. And in the previous video, we wrote down a matrix representation for that linear map. It's this. And if you look at this, it contains within it matrix representations for some interesting things. Here is a matrix representation of the identity map. It's called the identity matrix. Here is a matrix representation for, way back up here, for the derivative of f at x naught y naught subscript x. When we say subscript x, on the side of matrix representations, it's having the effect of taking the left half. When we say subscript y, it has the effect of taking the right half. So our assumption at the very top is that if I put in x naught for x and y naught for y, then this matrix in red here is invertible. That's our assumption at the top. And down here we have an identity matrix. So if I put in x naught for x and y naught for y, this whole thing here is definitely invertible. Why? Well, I'm about to show it in detail, but depending on how comfortable you are with different linear algebra ideas, it might be immediate to you right now. If this thing is invertible and this thing is invertible, it's the identity map, then, well, the determinant of this matrix, which is made out of these 4 blocks, right? I've sort of cut it here and here, and I'm viewing it as these 4 blocks. The determinant is this block times that block, is the determinant of this block times the determinant of this block. So this is a feature of, I guess you would call this a block upper triangular matrix, something like that. I don't know if that's an official term, but this is a feature of block upper triangular matrices. The determinant, for a regular triangular matrix, the determinant is the product of the entries on the diagonal. For a, let's call this a block upper triangular matrix, the determinant is the product of the determinants of the diagonal blocks. So the determinant of this matrix is the determinant of this block times the determinant of this block. Since we assumed this block is invertible, assuming you're plugging in x naught and y naught in for x and y, since we're assuming this is an invertible matrix, and the identity is definitely invertible, I'd be looking at the product of 2 non-zero determinants, which is non-zero. So the matrix as a whole is then invertible. Okay, I don't think that that will be satisfying to everyone. If you are happy with that, then and you don't want to see any other way of doing it, then go ahead and skip to the next video. But otherwise, I'll spend the rest of this video putting in order a different way of looking at it that doesn't use the word determinant and doesn't use any features of block upper triangular matrices. Okay, so what I've done here is copied the matrix above and then shrunken it down so I don't have to rewrite it, which is really nice that I can do that. I wish I could do that on a chalkboard. So for any given vector hk in Rn plus m, if I evaluate f prime of x naught y naught at hk, so if I take this linear map and I evaluate it, that vector, arbitrary vector, then I get this matrix applied to that vector. That's what it means to say this is that's what it means to say this matrix represents the linear map here in the standard basis. It means this linear map applied to a vector equals this matrix times the vector. So here, let me write the vector as it has an h portion, and so let me split up my column vector into this h portion and this k portion. And the h portion is consisting of n entries, and the k portion is consisting of m entries. Okay, so when we, and by the way, I've sectioned off this block in red. That block is basically is what you would call f prime of x naught y naught sub x. Oh, hang on, there's one little issue, which is I'm putting in specifically x naught y naught here, not x y. So I should zoom in on this and go fill in little not subscripts to make it right. Not that you can necessarily see it from that far away. Okay, that's done, although you can't really see from that far away anyway. So, okay, so what happens when you apply this matrix to this vector? So you're going to get a column vector out, right? This is an n plus m by n plus m matrix. So if I apply it to so this is a square matrix. If I apply it to a vector with n plus m components, then I get a vector with n plus m components out. So it has these first n components and these second m components. And these are as follows, just applying the definition of matrix multiplication. Excuse me. These are, so this first n components, this is what you get when you apply the top half of this to this vector. So that's going to be this red portion applied to h. So the red portion applied to h plus let me give it its own color. Let's make it yellow. Or, I feel like it should also kind of be red. No, I'll go with yellow. Okay. Plus this yellow portion applied to the vector k. And then down here we have, well, a big fat 0, right? For this applied to h, and then plus this thing applied to k. That's just k. Let me write it like this. It's just k. Okay, so what I've done here is used this breakdown of the matrix to describe what happens when the derivative of f at x naught y naught is applied to a vector, breaking the vector up as the h part and the k part. So here's what you get. You get this vector, which if you were to break it up, you would get this for its first part, and then k, just straight up k for its second part. So I could just write k here like this. Okay, so what I'd like to prove is that this is invertible, right? I want to prove this is invertible. So I will just prove it's injective. That will be sufficient, since it's a linear map from a vector space to a vector space of the same dimension. So if it's injective, then it's invertible. So if this applied to hk is 0, the 0 vector, meaning 0 is all the way down here, so this comes out 0 and this comes out 0, then k is 0. K must be 0 because we got zeros all here, so 0 is specifically for k. And if k is 0, then you also have this portion must be 0, right? this yellow matrix applied to k, that would also be 0 if k is 0. So since I'm assuming that what comes out here is 0, and this is 0, then I have red matrix applied to H is 0. So red matrix applied to H is 0. But the red matrix is, so let's have a look at the red matrix. The red matrix is the components of the derivative of f subscript x. Subscript x. So this here in my statement of the implicit function theorem, this linear map has matrix representation being that red matrix down there. And I'm assuming it's invertible, so I'm assuming it's injective. So then if applying it to H yields 0, then H must be 0. So since red matrix applied to H is actually the linear map f prime x naught y naught applied to H, subscript x applied to H, we have H equals 0. That should be part of this same sentence with the if, so how about I turn this into a semicolon. Therefore, this is injective and hence invertible. Okay, so that is what we needed. That's what we were going for up here. We needed these two things, and we now have them. We now have that we can apply the inverse function theorem to capital F. So it remains to apply the inverse function theorem and see what it provides, what the inverse function theorem tells us about capital F, and then interpret those results and see how it gives us the conclusions we want. So that will take some effort. So these were the conclusions of the implicit function theorem. Okay, so next time, applying the inverse function theorem.